Hi everyone, this is Mr. Lucas. So this week we are covering number systems. So the number systems in computer language equate to binary, which are zeros and ones, decimal, which are its binary represented in a decimal form, like the number 3 or the number 120, right? And then we have hexadecimal, and hexadecimal is numbers 0 through 9 and letters A through F. Okay, so remember those three vocabulary words: binary, decimal, and hexadecimal. So with number systems in Cisco, we're going to be converting between those three representations of information. And in particular, this matters to us in networking because this is how the router talks to the computer, how it talks to switches, and so on. So we have to be able to convert between them. It'll also become very, very important later in the semester when we cover IP version 4 and IP version 6 addressing in depth and start subnetting. So it's very important to get a firm grasp on binary to decimal conversion, decimal to binary conversion, and then decimal to hexadecimal conversion, and hexadecimal to decimal conversion. Okay, so let's get started. So an IP version 4 address, and remember we talked about in layer 3 of the OSI model, the network layer, or in layer 3 of the, or really it's layer 2 of the TCP IP model, which is the internet layer. So remember, layer 3 of the OSI model is technically layer 2 of the TCP IP model called the internet layer, but let's stick with the OSI representation. So layer 3 and the OSI model is the network layer. So the network layer is concerned with IP addressing. So you either have IP version 4 addresses or IP version 6 addresses. So remember, as it goes up and down those layers of the OSI model, it basically puts a little box around each set of information as it passes it down. All right, from the application layer, from layer 7 at the top all the way down through layer 1, and then it hops on the cables and turns it into zeros and ones, right? But layer 3 is really concerned with IP version 4 or IP version 6 addressing, okay? So let's look at what that data encapsulation looks like at that layer and what information is added. So an IP version 4 address has 4 sections separated by dots or periods. So you're probably used to those. You've seen those. They may be represented like a 192.168.1.1. All right, like that. So with them being represented by decimal numbers separated by dots, each section is 8 bits long, and I'll show you that in a second. And each section is called an octet because each section is 8 bits long. So this section is 8 bits long, this one is 8 bits long, that one is 8 bits long, and so is that one. No matter if it is actually what number is in there, it is 8 bits long. Okay, so those 4 sections at each 8 bits long, each section makes an IP version 4 address a total of 32 bits long when you look at a total entire IP version 4 address. Okay, if I turn this sideways, I've gotten written out here. All right, each section, all right, you see the period in between each one. So this is section 1, 2, 3, and 4 here. Each section can be, and it has 8 placeholders here, or 8 bits. So each one of these can be a 0 or a 1 in computer language, right? And these values at the bottom are always the same. So it goes 128, 64, 32, 16, 8, 4, 2, and 1. All right, if you notice, it halves every time and it starts over in every section. So 128, half of that is 64, half of that is 32, half of that is 16, half of that is 8, half of that is 4, half of that is 2, half of that is 1. Then it does that repeatedly all the way down. If you count these placeholders, there are 32 placeholders here, okay? That's where we get the 32 bits long, and each one of these can be a 0 or a 1, okay? So if it is a 0 in a placeholder, we don't really count that value, if you will. If there is a 1 in that placeholder, we do count that value, and I'll show you what that means in a second, okay? So this is in binary, either zeros and ones. So each section in binary can be a total of 255. So if we add all of these numbers, that means a 1 would have to be in each one of these sections. If we add all of these numbers together, then we would get a total of 255. Okay, 128 plus 64 plus 32 plus 16 plus 8 plus 4 plus 2 plus 1. You can double check me on a calculator. It would be 255. So that's the max number we can get in each one of these sections. So you would never see it say 256.256.256.256. Can't happen. The most it can be is 255.255.255.255. Okay, so it can be any number between 0 and 255 in each one of these sections. All right. Each placeholder again has a 1 in binary to actually equal that 255 in decimal. If it had a 0 in each one, then it equals 0. And we'll show you kind of how you make up all the numbers in between. Okay. So if each one of these placeholders can be a 0 and 1, this is just one section, okay? So you see there's 8 bits here. Just imagine this is one section of an IP version 4 address. The reason we have these if you go down or double them if you go up is because we look at them as a value, an exponent of 2. So 2 to the 0 is actually 1. 2 to the 1 is 2. 2 squared, or 2 to the second power, is 4. 2 to the third power, or 2 cubed, is 8. 2 to the fourth power is 16, 2 to the fifth power is 32, 2 to the sixth power is 64, and finally 2 to the seventh power is 128. Okay, so remember, each time we have these 8 placeholders in each section, we can write this value below each placeholder, okay, or each bit. You need to memorize that. So memorize and burn that in your memory banks: 128, 64, 32, 16, 8, 4, 2, and 1. And it starts over for each section. Okay, so make sure you burn that into your memory banks. If you have a 0 in that placeholder, you do not count that value in your decimal conversion. If you place a 1 in that placeholder, you will count that value in your decimal conversion. Each placeholder is a bit, so 8 placeholders is 8 bits, okay? And we've got 4 of these sections, so that equals a 32-bit address. So let's take a look at how we would actually apply this information that we've just learned. So if we have the value, the decimal value of 13, how would we actually make that in binary? So again, we've got our 8 placeholders here in binary, and each one has a value, remember: 128, 64, 32, 16, 8, 4, 2, and 1. And up here, each one of these can be a 0 or a 1. So to make the number 13, which of these values can we add together to make up 13? Remember, we can make up any number we want from 0 to 255. So 13 is achievable. So if we take 128, right, that's way too high. So we don't need to start there, because 128 is way higher than 13. So that's probably going to be a 0. 64, same thing. 32, same thing. 16, same thing. All right, now let's look at these. So 8 plus 4 equals 12. And then plus 1 equals 13. So let's put a 1 in these. All right, and then we can go back and fill in anywhere else we need to enter a 0, because we're not going to use that one. So we're adding together the 8, the 4, and the 1, and that equals 13. So we put a 1 in those placeholders because we're adding those values together. So in binary, if we want to write or represent the number 13, then we need to do 0, 0, 0, 0, 1, 1, 0, 1. All right, so this is the binary representation of the decimal value 13. All right, let's try another one. This one is 148. Okay, so again, all of these are lower than 148, so everybody's kind of game to be added together to equal 148. All right, so let's look at what could we add together. So 128, to get 148, we're probably going to have to start with 128. All right, but let's just see here. So 128 plus 64 is 192, so that's too much. 128 plus 16 is 144, and then if we add 4 more, that equals 148. So if we do a 1 here, then a 1 here at 16, and a 1 at 4. All right, and you can double check me with the calculator, right? 128 plus 16 is 144, and then plus 4 more equals 148. So if we go back and fill in with zeros where we don't need it, then we end up with 1, 0, 0, 1, 0, 1, 0, 0. So we are adding together 128 plus 16 plus 4, and that equals 148. All right, see how we get that? So our answer would be 1, 0, 0, 1, 0, 1, 0, 0. All right, let's try some more examples here. So that's going from decimal. We start at decimal and go to binary. All right. So this decimal value is 192. Okay. So what would we need to add together to get to 192? All right. So you may have just kind of clued in from our previous example, but I said 128 plus 64 is 192. So a 1 there and a 1 there. That equals 192. So everything else we can place a 0. All right. So we end up with 1, 1, 0, 0, 0, 0, 0, 0. Right? So that equals 192. All right. Let's try 220. So if we've got a value of 220, all right, which one of these values could we add together to equal 220? All right, so let's see. 128 plus 64 is 192. All right. And again, you may not want to put a 1 there in your answers as you're working them out. You might just want to kind of keep a note of which ones you're doing. So 128 and 64 is 192. If we added 8 more, that'd be 200. Then if we need 20 more, then we do 16 plus 4. All right, and that equals 20 more. So, all right, so 128 plus 64 is 192. If we add 8 more, we get 200. We add 16 more, we get 216. We add 4 more, we get 220. And then we can fill back in with zeros right there. So our answer in binary for the decimal representation of 220 is 1101100, and that equals 220. All right, so we've just done several examples of going from from decimal to binary. Now let's complete some examples of going from binary to decimal instead of decimal to binary. Okay, so if we are given a value here of, let's say, all ones, and if you were paying attention earlier, you should know that that equals 255, right? Because we are literally adding every single one of these values together, right? So we're adding all of them together till we get 255. So our answer would be 255. So if we saw all ones there, our decimal representation of that would be 255. Okay. What if we had 1, 0, 0, 0, 0, 1, 1, 1. All right. So we're going to add 128. We're going to add 4, 2, and 1. Right. So we're not going to add everything, just 128, 4, 2, and 1. So if you add all those together, you should get 135, because it's 128 plus 4 is 132, plus basically 2 is 134, plus 1 is 135, which is our decimal representation of that in binary, right? Then let's say if we have 1, 1, 1, 1, 1, 1, 0, 0. All right, so we're adding together 128, 64, 32, 16, 8, 4, and that's it, right? Now, there's a couple different ways you can approach this. Again, you can add all those together, and you should get 252 as the decimal representation. Okay. Now, if you know, though, that if they're all ones here, that it equals 255, what you could do is say, oh, okay, well, if I don't have a calculator on me handy, the easiest way to do this would say 255, let me minus 3, basically. The 2 and the 1 have 0, so let me minus 3 to get 252. All right. So let's try one more example. Let's say if we have a 2, 3, 7, 8, 128, 64, 32, 16, 8, 4, 2, 1. Let's say our binary value that we want is 0, 0, 0, 0, 0, 0, 1, 1. Right? So with that one, we're just adding 2 and 1 together. So that equals 3. Right? So 3 would be my decimal representation for 0, 0, 0, 0, 0, 0, 1, 1. Right? If I have all zeros, what do you think that would be? It'd be a 0. Right? So you see how we can make any number between 0 and 255 between decimal and binary. All right. Now we get into hexadecimal. So IPv4 addressing uses numbers 0 through 255 in each of the sections. Again, that equals 32-bit address. Also, if you remember, we've talked about and you've seen in the Cisco Networking Academy that the IPv4 addresses are pretty much depleted, meaning ran out, especially in the American Registry for Internet Numbers, or ARIN, A-R-I-N. So there are no more backbone internet IPv4 public addresses to really give out to internet service providers or companies who need them. So we created IPv6 to handle that. IPv4, there's only about a little over 4 billion possible addresses. If you minus out the private addressing space, there's only about 3.7 billion. But if you've got IPv6, that's actually 340 undecillion addresses, which are a lot of zeros after the 340. So we should not run out anytime soon or anytime in the near future. So with the IPv6 address, though, it's much longer. An IPv6 address is actually 128 bits long, where an IPv4 address is only 32 bits long. There are actually 8 sections instead of 4, and each section there are 4 digits. Now, each digit can be a number 0 through 9 or letter A through F. All right. Each section is called a hextet instead of an octet. Octet is 8 bits per section. A hextet, like in this, is actually 16 bits long. So if you've got 8 sections of 16 bits, you get to 128 bits long. They're also not separated by dots. It's actually separated by colons. All right. Each hextet is, again, 4 hexadecimal digits. And each of those 4 digits can be a 4 placeholder binary representation. So how does that kind of break down? So I just put X's here because, again, these addresses can be really long, okay? But I just kind of put X's here to represent the 8 sections. So in, like, let's just say this one. In this section, there can be 4 digits, either a 0 through 9 or A through F, 0 through 9, A through F, 0 through 9, A through F, or 0 through 9, A through F. Now, to represent this in binary, if you do have a 0 here, or a 9 or an A, whatever that one digit happens to be here, then it can be represented in 4 digits of zeros or ones. So that means that each one of these are 4 bits. So 4 bits times 4 digits is 16 bits for each one of those 8 sections. Okay, so that equals 128 bits long. So what it could look like is, again, this one section here could, in an IPv6 address, looks like maybe 1A3F, 013A, FFEB, all right, and so on and so on and so on. So if each one of these right here can be broken down into 4 bits, right, each one of these, then we end up with 16 bits per section. Okay, so again, remember before we had 128, 64, and we halved it down through 1 for those 8 bits in IPv4. Each one of these has a value of 8, 4, 2, and 1. So if you notice, the biggest number we can kind of make here is 15, but we're actually not making decimal numbers, we're making either letters or numbers 0 through 9. So if you actually wanted to make, let's say, a 1, then you're actually going to do 0, 0, 0, 1. That adds up to 1, right? Now, if we want to do 3, you do a 1 here and a 1 there, because 2 plus 1 is 3. If you want to do an A, so what happens is with our chart, let's get our handy dandy chart out, and I'm going to put this in your notes. It's available in the Cisco Academy. All right, what happens is, all right, you see here we've got our hexadecimal and we've got our binary values. So what happens is here at A, that equals 10. So that's the 8 placeholder and the 2 placeholder. So 8 plus 2 is 10 equals A. 11, 12, 13, 14, and 15. Okay, so you can kind of think about that. 10, 11, 12, 13, 14, and 15 in terms of decimal. Okay, again, that's the decimal representation. So, and we'll get there and practice that in a minute. So when you are converting between decimal to hexadecimal or hexadecimal to decimal, you always have to go through binary in the middle. That's why it's very important to know binary. So if we start out with 168 in binary, okay, 168 in binary, if we do our 8 placeholders, 128, 64, 32, 16, 8, 4, 2, and 1, that's why it's important you know these vocabulary words. The decimal value is 168. The binary value, and when you hear decimal, you should think that, right? These 8 placeholders, 128, 64, 32, 16, 8, 4, 2, and 1, okay? So I know to make 168, I need a 1 here, I need a 1 there, and I need a 1 there. Okay. Now, in step 2, all right, if I split these in half into 2 groups, basically splitting it right down the middle, because again, remember my binary binary for hexadecimal is only 8, 4, 2, and 1. So it's half the amount of digits, right? It's only 4 instead of 8. So if I half that down the middle there where I drew my blue line, I would split it into 1, 0, 1, 0. 1, 0, 1, 0, and 1, 0, 0, 0, 1, 0, 0, 0, right? So I'm literally just splitting it right there, okay? So what is 1, 0, 1, 0 in hexadecimal? A, all right, it equals 10. And then 1, 0, 0, 0 in hex is 8, because that is a 1 in the 8 placeholder, right? So if I drew my little placeholders there, that's 8, 4, 2, and 1. If I draw them here, 8, 4, 2, and 1. Okay, so that equals, or you could just look at your chart. All right, 1, 0, 1, 0 is an A, 1, 0, 0, 0 is an 8. So if my decimal representation is 168, my hexadecimal representation is A8. So when you see A8, it is the exact same as 168. All right. Now, what if I was given D2 in hexadecimal? And you'll always be told what the actual value is in, okay, what form it's in. So in binary, D is 1101 and 2 is 0010, okay? So 1101 and 0010, those two, if I put them together, it's basically like adding them together to make one long 8-bit one in one group, then I get, all right, and if I know I'm trying to get the decimal, I put my values right here, 128, 64, 32, 16, 8, 4, 2, and 1, and I put my 1 placeholders the way that they've got them already, then I just add up 128, 64, 16, and 2, and I end up getting 210. Okay, so D2 in hexadecimal is actually 210 in decimal. All right, so let's practice a couple of these out. So if my decimal value is actually 210, then let's get to our hexadecimal value in the end. So first we need to think about what is 210 if that's decimal. All right, write those out, 128, 64, 32, 16, 8, 4, 2, and 1. When we think of decimal, we should think that, okay? So what do I need to put in zeros and ones in these placeholders to get 210? So I do 1, 1, 0, 1, 0, 0, 1, 0. All right. Then I'm going to split them right down the middle. We're giving 4 and 4 bits on either side of that line. So in hexadecimal, okay, if I do 1, 2, 3, 4, 8, 4, 2, and 1, I end up 1, 1, 0, 1, straight from there. And then over here, 2, 3, 4, 8, 4, 2, and 1, I end up with 0, 0, 1, 0. Okay, so that one you should be able to tell that's a 2 over there. And then this one over here, again, if you want to look at your chart, you certainly can. And if I look at my chart, I'm looking for 1101. So 1101 is 13, or it is a D. Okay, so based off my chart, it should be D2, which is the example we just did. But the hexadecimal value is D2 for the decimal value 210. All right, let's look at one we don't know. So if my decimal is 61, so for 61, I'm going to put a 1 at 32, 16, 8, 4, and 1. I'm going to go back and fill in zeros everywhere else. So 32 and 16 is 48, plus 8 more is 56, plus 4 more is 60, plus 1 is 61 there. All right, so that's my binary. Now, 1, 2, 3, 4. I'm trying to get to hexadecimal, so I know I have to write this out. When you think of hexadecimal, you should think 8, 4, 2, 1, 4 placeholders. 1, 2, 3, 4, 8, 4, 2, and 1. And I'm going to draw a line to split these one more time. And so I've got 0, 0, and I'm just taking this directly down there, and I'm taking these directly down here. Okay, so if I look at this, that should be a 3. So it's got a 1 in the 2 placeholder and a 1 in the 1 placeholder. So that should be a 3. All right. And then this one over here is 1101 again, just like that. So I know that one's a D. So this one should be 3D in hexadecimal value to equal 61. All right. So now let's look at what if we have hexadecimal first. All right, so I've got 2C. So we're always going to binary in the middle. All right, so to equal that, if I do 1, 2, 3, 4, 8, 4, 2, and 1 here. All right, so to get a 2, I need to have a 1 there and zeros here. Okay, to do a C, all right, I need, so this is my 2. Okay, to do a C, all right, 8, 4, 2, and 1. All right, to do a C, I'm going to do 1, 1, 0, 0, which would equal 12 here. But again, you can consult your chart here. So I'm looking for 1, 1, 0, 0. All right, 1, 1, 0, 0 is 12, or C right there. Okay, so C. So I know that's a C there. So I'm going to bring these down. So that's if they were split up, right? So I'm going to bring them down here and put them 0, 0, 0, 0, 1, 0, and then 1, 1, 0, 0, right in order, like I'm combining them together. Okay, so now I'm just going to add those values. 32, 8, 4. So what is 32 plus 8 is 40, plus 4 more equals 44 in decimal. So 44 in decimal equals 2C in hexadecimal. All right, so using this, we can go anywhere we want between decimal to hexadecimal, going through binary in the middle. We can do hexadecimal to decimal, again going through binary in the middle. And we can go from decimal to binary, binary to decimal. We can go from hexadecimal to binary, and binary to hexadecimal. They just have to tell you what they're looking for, and you have to know what you start with. All right. And again, make sure you consult your chart if you have any trouble with that, with the hexadecimal conversion values or anything. But that's it. So now you have a firm foundation of the number system.